Okay, so this is an online quant test for a quantitative trading role, effectively to be a quant trader at this company for crypto. I've got no idea what is in this test, so this is all effectively brand new to me. I'm going to go through this live. I get 90 minutes to do the test. I don't know if I'm going to pass or fail. I'm going to record everything in real time. So let's just read what's here. I literally haven't even read anything. So nice to meet you and my name. Nice to meet you, Darren. As part of our assignment, you need to finish one quiz. This is a crypto trading firm, by the way. I've traded for 20 years and they gave me a child's test. I did get a sample question previously on email, and the question was something like, you've got 25 snails, pick the top 3 snails. You're allowed to do races of up to 5 snails and pick the top 3 snails, the fastest 3 snails in the minimum number of races possible. I believe the answer to that was 7. So a bit of a baby question and not really relevant to trading, although I guess there's some sort of concept of the mathematical mindset. Doesn't make one a good trader, but nonetheless that seems to be the hurdle for this particular firm, almost like it wants to filter out, I guess, geeks. I'm not sure I fall into that category or not, who knows. So each quiz has its own deadline that starts counting down once you press the take the challenge button on the next page. 2 timers will show how much remaining time you still have. So I guess I would have to click this and the countdown starts. The remaining timer shows you the intended time for each quiz. Okay, so I guess each question, when I say each quiz, there must be each question has some kind of time scale on it. You should be able to finish your assignment within this time. Successful submissions made while the remaining timer is ticked is earning you extra points. Successful submissions made while the remaining timer is ticking earns you extra points. So presumably if you finish within the time for a specific question, and I don't know how long these questions are, so say a question's 3 minutes and you finish it in 2 minutes, I'm guessing that you get some sort of bonus points for that. And then I presume you just move on to the next question. The finishing timer starts counting down once the remaining countdown expires. It gives you a few more minutes to finish your assignment while signalizing the real deadline for your assignment. When his timer falls to 0, you will no longer be able to resubmit your answers. So it suggests that you can submit answers multiple times by the looks of it. So I guess I should submit something, even if it's wrong, and then iterate on it and resubmit something if it's better. The first part of that, I don't know, either it's written in bad English or I don't fully understand it. The first timer starts counting down once the remaining countdown expires. The finishing timer starts counting down once the remaining countdown expires. It's really not clear. I guess maybe it's a sample question or something with a sample, so like a couple of tests or something. You can resubmit any of your solutions as many times as you like, as long as they are within the time limit. Your answers are saved periodically so that even in case of technical issues, we might still know how well you did. Okay, I don't know if that means if you haven't finished something, if that's auto-submitted or not. Quizzes you need to finish are marked with a cross. The ones you've already submitted are marked with a check mark. The test is 90 minutes, I know that, so it's an hour and a half of wasted life. for the first round interview of a firm that then asks you more potentially silly questions, I guess, in a second round interview, and then does a third round interview, only to discover that they've lost 25% of their capital through FTX, and all of these questions were meaningless. So I can't tell how many questions, it doesn't say here how many questions are going to be asked. I'm told that the test is a maths test. So I have a piece of paper. I was told to have a piece of paper and a pen, something that I've not done for ages, because normally I do coding stuff. That's the way that the world is, but this is maths. I also am armed with ChatGPT, which I will be using, because if the questions are silly, not silly, probably the wrong word, but if the questions are answerable via that, then I'm going to use a tool available, because I don't want to waste time. So I'm just deleting lots of things. I've got ChatGPT here. I'm going to use it, because I'm not going to reinvent the wheel for questions on snails racing. Let's Python if statement. Oh, I'll keep a couple of those things up, but I'll have a new chat available. So hopefully I'll be able to copy and paste some questions in. I'm armed with Google Bard. So I presume, I don't know if one's going to be better than the other. Maybe I'll get some sort of corroboration. That's assuming I can copy and paste out of the website into these applications. And if I have to re-explain them or use them in some way, so I've got those to the side. I will also open up or have a spreadsheet available to the side so that I can do some calculations. I might as well. Saves having a calculator, but I do have a calculator here somewhere too, which is over here. So that's my preparation effectively. So I've got all of the components that I need available to me. And I don't think there's anything else that I need. So my head's going to be down for 90 minutes. I've probably spoken for 10 in prep. Yeah, I've spoken for about 10 minutes in preparation. My head's going to be down for the next 90 minutes, attempting to answer questions. I will attempt to talk through them, but I don't know if I should or shouldn't, because it would be nice to pass, but I have no idea as to how easy or hard it will be. The oddest part, or the hardest bit, at least to start with on these types of things, is you don't know what you're expecting as a question, as in I literally don't know how many questions there are. I'm not sure about this finishing timer starts counting down once the remaining countdown expires. So I'm not sure exactly what that means. I guess it'll become obvious when it's there. The two timers. This is odd. Two timers will show you how much remaining time you still have. Why two timers? Two timers will show you how much. Each quiz has its own deadline that starts counting down once you press the take the challenge button on the next page. Why is there two timers? Why not one timer? So are there two different timers? I don't know. Is one timer for the global time of the whole 90 minutes and the other timer for the question? I don't know. It doesn't say that here. That might be logical. I don't know. So I think basically I'm going to have to start the quiz and see how it goes. Oh, and I forgot to add that. Let's have a look. yeah, we are ticking on. I forgot to add one thing, which is that even if I was successful, this job is in another country. So I'd be moving from England to Slovakia to do this job that requires this 90-minute quiz. So something to look forward to. Fantastic. So I now hit the start button and off we go. Let's see what happens. Right. Welcome to Winston. In the quant team, one of the most important skills is probabilistic thinking. So this is about probabilities. That is why we came up with this test. You can expect 10 questions. There we go. You can expect 10 questions focused on calculation of expected value. To pass the test, you need to solve 7 out of the 10 questions. So you got 9, I guess you get 9 minutes per question. Just because over here we've got 90 minutes. Just things that we need to know. 90 mins. Right, and you've got 10 questions. So we have that many minutes per question. So basically just under 10 minutes per question. I hate the auto capitalization. So we've got 10 minutes per question and we need to get 70% of them right. The test will be reviewed by our quant team, which usually takes 1 to 2 days. It's that old school marking. A couple of tips. For each question, your answer should have 2 parts. A correct result, followed by a short explanation of how you came up with it. We encourage you to use intuition. Before you start, we recommend going over all the questions. Some are easier, others more difficult, and you can choose which one you want to tackle first. Try to find a place and time where you will not be interrupted during the test. So, I don't know, 9 o'clock at night on a Wednesday afternoon where I could be doing potentially better things. This is a good time for me not to be disturbed. Okay, so my phone is on silent mode to make sure I won't be disturbed. And there's a cup of coffee here. There we go. Cappuccino. I'm going to hit the take the challenge button and see what happens. I might be quitting after 45 minutes for all I know, but let's just see what happens. Here we go. Right, it's quiz. 10 low to medium complexity problems based on your understanding. However, try and write a solution for every problem, even though you're not 100% sure or didn't have time to solve it. Please only use a pen and paper and don't cheat. I'm not sure that don't cheat means that you randomly break a stick into 2 pieces. What is the expected length of the smaller piece? I mean, I'm going to guess that that's 50%. Right, okay, much more complex answer to that, which is this. Assuming that a stick is broken in at a random point, the length of the stick can be modelled as a continuous uniform distribution over the interval 0 to L, where L is the length of the original stick. Let X denote the length of the smaller piece, then the probability density function is given by this, right? Okay, I mean, this is silly in a way. The answer is 50%, really. Well, sorry, the expected is half of 50%, I guess, because 50% is your piece can't be the smaller piece. It's got to be quarter, basically. But you're going to see why, but this is intuition. The half the piece is going to be L over 2, basically. So, right, basically, that's the answer. You know, pretty much that's it. And then where do you hit submit or whatever? Remaining answered 1. Right. I don't know what finishing means, or where you hit submit. However, try and write a solution. Please only use a pen and paper. You have 1 hour to complete the test, which is different to 90 minutes that it said on the front. But there's no submit button anywhere. So is there a submit button down the end? Oh, that's submit quiz. So I don't know if it means that. You rolled a fair 6-sided dice and you receive £1 for every dot landed. What is the expected profit? Right. Well, it's 6 plus 1 to the 5 plus 2 and so forth. It's a number of dots divided by 6 basically. So there we go. Again, something that I could have guessed or got quite close to without needing to be a quant. Because it's roughly half of the 6. Basically, it's 7 plus 7 plus 7. I guess it's half of those, which is 3.5 of each. That divided by 3. So, right. You play the previous game, but you can re-roll the dice. If you don't like the result, what is your expected profit now? You can rewrite if you don't like the result. Okay, so basically it's going to be higher than 350 and lower than 6, and it's going to be somewhere, I guess, halfway above that. So it's going to be about 475. And copy that. I mean, you know, I guess you could be a mathematician for this, and I could go through the whole rigorous proof. Not bad as a guess, right? Okay, I mean the rigorous proof is here, which is the 1, 2, 3, 4, 5, 6, and you get to throw out the ones that are like less than 3.5 because they're not optimal ones. So like that's why I was already guessing that it'd be 475. The total answer is 425. Maybe there's some crudities in what I need to do. I'm not even going to look at it, quite frankly, because it's I'm not going to say it's child's play. You need to know the answers to these sorts of things and how you derive them. But I think the overall understanding of the physics of it and possibly the maths of it is what's important here. You toss a fire coin 100 times. Seen this one 1,000 times. What is the probability that the number of heads will be divisible by 2? Okay, that's a bit more interesting in a way, because your expectation is for like 50-50, and that's divisible by 2, but you could get a 49-51, so that's not divisible by 2. So it's the probability distribution, but all of the even components of the probability distribution. That's what I'm expected ChatGPT to pick out of this. So let's just do this as parts, right? Which is this. Number of heads obtained in a coin toss follows a binomial distribution. That's a binomial distribution, so that's correct, assuming the coin toss is fair. Let X denote the random variable representing the number of heads in 100 tosses. It says remaining time. 1:23. Okay, 1 hour and 23. Looks like you got 90 minutes. One plight said 60 minutes. The probability that the number of heads is divisible by 2 is the same as the probability that X equals even. Yeah, and this can be computed as, right? So, you know. So let's take all of that and paste that in here, right? The probability that it's even is the probability that X equals 0 plus the probability that X equals 2 and probability that X equals 4, all the way to the probability that X equals 100, right? So, and all of the odd ones don't count. So probability that X equals 1 and so forth and X equals 3 don't count. Using the binomial probability formula, we have probability that X equals K is 100 choose K. Yeah, that means that's like NPK basically. That's what the choose thing is. Like if I was banging it out on a calculator, 0.5 to the power of 100, where 100 choose K is the binomial coefficient, which gives the number of ways to choose K items from a set of 100. Okay, yeah, I mean, there we go. Right. I'm just reading these because it's actually interesting seeing the answer. Probability that answering the actual question is immaterial nearly. The probability that x equals even is 100 choose 0 times by, yeah, okay, yeah, it's literally just a standard binomial distribution. The half to the power of 100 is because you need to get nothing 100 times, so it's a half to the 100. This will be the n choose 2 will be the same thing. Each one is that to the power of that. So right, simplify the equation as that. Right. The funny thing is intuitively again, I don't know if it's logical or not, but the answer is kind of like there. What's the probability that the number that we get as an outcome is divisible by 2? It's half of the outcomes, because the other half of the outcomes are that it's not divisible by 2. Now, if it wasn't half, I would expect it, and this is from a physics perspective, I would expect it to be damn close to a half, as in like maybe it didn't capture, some of like a pair of the outliers of the evens or the odds, but that's all it could be out by because of the symmetry of it. So there's a lot of mathematics to get round to an answer that one might argue is very, very logically intuitive. But I like the maths. I'll go through that another time because I want to be a legend finishing quickly. Right. In Quantera, parents breed kids until their first boy is born. Some families say, okay, I've actually worked this out with my kids because I've got 3 girls. What's the probability of having 3 girls? Right, it's a half times a half times a half. It's 1/8. And the probability of having 3 children of the same kind, like 3 boys or 3 girls, because my sister's got 3 boys, and the probability of her having 3 boys is 1/8. And people say you've got 3 girls, so that's so unlikely. It's not. It's actually 1/8 because it's a half to the power of 3 because they're the combinations. If you plotted all those combinations out and printed them, then you would find that 1 of 8 options exists basically, and therefore it has to be 1/8 as assuming everything is equally likely, which everything is equally likely. I'm going to paste the question in now into there, and this whole thing about Quantera is a bit silly. Until they're first born, some families have a single boy, some families have 15 daughters and 1 boy. Assuming there's a 50% chance for every single pregnancy to end up as a boy or girl, what is the ratio of boys to girls in Quantera? So basically, it's kind of like your expectation of how many boys you're going to have until you get a girl, because you could, as the question rightly says, have 15 daughters and 1 boy. That's a diminishing probability, as in you've got a half to the power of 15, and then, 15 daughters and 1 boy is a half to the power of 16. Is a number of is the probability of that occurring, basically. It's going to create some sort of log normal distribution in a way, I'd imagine. Massively long answer to this question. Way longer than I would do, and I don't know how I would write this all down on a piece of paper and do something. And the thing is ChatGPT for this kind of thing is just far superior to what I could produce on a piece of paper, or, by the way, anyone else could produce on a piece of paper. Now, let's go to the final part. The ratio of boys to girls in Quantera is 1.364. Now, that's an interesting one, but yeah, there's going to be more boys than girls. Now, why is that the case? Because if you've got 1 boy, then you've stopped. You're always going to stop at a boy, basically. So the probability of having 15 girls and one boy, so the probability of that ratio being 15 times effectively, or approximately 15 times, is a half to the power of 16, which is, let me pull this up somewhere, it's going to be this, 0.5 equals, I'll do the power, POW, there we go, power, this, comma, right, pounds. That's the problem. Let's have a look. How does this power function work? Right, A to the B. This one, I would expect that one to be 16, but when I did that, it said name. Right. Okay, equals this one, because I'm not mucking around with it too much, so the power of 16. There we go. And I'd kind of like have to increase this, right? Like loads. There we go. Oops. It's this minute probability that you have this imbalance, and you'd have to so that would give you a ratio of 15 to 1, or 15 to 1 with this tiny fractional probability. So, but the probability of having one boy and no girls is 50%. So you could have one boy, 0 girls, right, and that's got a weighting of 0.5, right? Now, and you've got all of these scenarios in between. So let's expand this. So you've got all of these, one boy. Here is the probability, and I should maybe move these across, I guess. X, V. I'll move it over to there. X, V. Right. This here is it's actually 15 girls and one boy. Each one ends with one boy. Just for the record. Don't like that one. Everything should be size 10 there. Right, there we go. I'll make it all size 12. I think that's what it was. Right. And then you've got all of these ones in between. So you can see now that it's kind of like the sum of all of these will be, so you'd have 2 boys, 1 girl, so you'd have 1 boy, 2 girls, and so forth with diminishing probability. So it'd be 1 boy, 2 girls. And then 1 boy, 3 girls, and so forth. But the probability of that is 0.5 times 0.5, and then time. So that's 1 boy. 1 boy. You'd have 1 boy, 1 girl first. Should have. I won't muck around with it too much because I want to get to the end of it. But you'd have this basically: 1 boy, 1 girl. X and B. Paste it down there. But you'd have 1 boy, comma. I don't know why they're going. 1 girl. There we go. Somewhere in between. Don't know why that goes to, which is annoying. 12 slows me down. 1 boy, 1 girl, and so that would be 0.25, and this would be 0.125, I imagine, because you need to have a girl, and then a boy. That's the only options for it. So, right. And so forth, and it'd be the sum of all of these, and that's your expectation, and your expectation, therefore, or you need to get the ratio, and it's of boys to girls from the outcome, and that's what it would be basically. So I'm going to leave it at that. I'm quite happy with the answer. Right, now let's go. You are playing Russian roulette. There are precisely 2 bullets in neighbouring chambers of a 6-shooter revolver, so if you've got a 1/3 chance of being shot in some way. The first person spins the barrel, pulls the trigger, and the gun does not fire. The gun does not fire. You are next. It means the gun fires and you're not killed, I presume. So you've got, what, like 5 things left, possibly? Or no, or you're just next. Well, you've got the same probabilities, actually. That's not going to diminish your probabilities. I'm going to go for a 1 1/3. The first person spins the barrel, pulls a trigger, and the gun does not fire. You are next. You just pull a trigger without spinning. What is your chances of dying? Okay, that's an interesting one. If you don't spin the barrel, why? I'll copy this one. Right, in this scenario, if you don't spin the barrel, the probability of dying is 2 out of 5. Has that one actually been shot then and didn't go? Because it doesn't say that. It says the first person, well, it should be spins the barrel, pulls the trigger, and the gun does not fire. Does that mean it fires a blank? You are next. You just pull the trigger without spinning. What's the chance of you dying? If the gun didn't fire, how would you know? This is because there are 2 bullets out of a total of 5 remaining chambers that could be aligned with the firing pin when you pull the trigger. If you do spin the barrel, the probability of dying is slightly lower at 2/6 or 1/3, which is approximately 0.33. This is because there are 2 bullets out of 6 chambers. Okay, I'm going to remove this because that's not relevant. So that's kind of like the answer. Let's go to ping pong. You play ping pong, the score is 10-all. The first one to gain the lead by 2 points wins. Your chance to score a point is 40%. For your opponent, it's 60%. What is your chance of winning? Oh, your chance of winning is not high. It's not. You don't have a 40% chance of winning. You're going to have a way less than 40% chance of winning. Hold on, the first one to gain the lead by 2 points win. Okay. Okay, this is going to be a probability distribution. Because basically, in order for you to win, your chances are 0.4 times 0.4. That gets you a win in one of the series, but like they might win one first and then you win the next 2, which is 0.6, and you'd have to count out all of the outcomes, and then it'd fall back to one of these types of binomial distributions, and you'd find a pattern and count that out, and that would give the probabilities. Right. So you can have this indefinite outcome. This is much more complete again. I couldn't do all of this in that period of time. It's just not possible. But these are basically all of the outcomes that you can have. And it's literally just counting through them. I'd actually take a brute force approach, but there is a mathematical approach too. So the probability of this specific sequence is 0.4 times 0.6 times 0.4 times by 1, right? You have to count all of these sequences. For example, you could win 13-12, 14-12, 13-11, and so on, right? Right, here's the recursive approach. I'm honestly not sure why this really although regenerate response, because let P be the probability of winning a game from this state. Right, I might just take all of this answer because it's the complete thing. And I will take this and I'm now going to put it into Bard. I've just pasted that question into Bard. And Bard does its little bit of thinking and it's going to bang out something. So there are 3 possible scenarios for you to win the game. You win the next point and your opponent does not win the next point. The probability your opponent wins the next point and you no, that's totally unsatisfactory as an answer. I mean, this Markov, I got a Markov on from the thing. I've put it into both here. You need to win by 2. There are 7 possible scenarios for you to win this game. That's not true. There's not 7 possible scenarios. There's much more than 7 possible scenarios because you can have like an infinite number of like a win, a loss, a win, a loss, a win, a loss, and that can go on for a lot of time. And so there's multiple scenarios. So this is not correct. Right. Right. I might hit a refresh button on this because it's not answering it very well, and I'll go back into this ping pong thing and I will copy that and paste it in and see if I can get a better answer out of there. It's giving me some Python code. Right, now I want Python code. The answer is spelled out. It's actually quite a nice answer here, because I would actually take this kind of approach when I said I do brute force simulation of a game. Your score is 10, the other ones, and you want to keep going on with this random thing, 0.4, and you can run it and you can do like 100,000 trials, and then you can print your chance of winning, and your chance of winning like basically will always end up being this kind of answer, which is 23.79%. Which sounds about right. Again, I'm going intuitively because it's not 50-50, because if you were equally be 50-50, the minute it starts dropping to like 40-60, the percentage chance of winning reduces dramatically, because on average the 60% one is going to win way more. He's not going to just win 60% more, because it's in order for him to not win, you would need the entire sequence of like loss, 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 win. So it'd be something like that. I'm just going to say I'm going to have to overwrite it. Right. I'm just going to paste that in there, and it's going to be about 20%. .6 squared, right? Should be the other way around. I'm just going to leave it there. I'll be questioned on it, but you know, I might come back. I could come back to that. I've still got an hour left, so. Treasuries. There are four treasures. There are four treasure chests. One of them contains $100. The other three are empty. If you pay a fixed fee, oh, I've seen this question loads. Normally we're shooting someone or something. It's the opening the box question. It's quite an interesting one. If you pay a fixed fee of X, right? If you pay a fixed fee of X, you can open any of the chests and take everything you find in there. If you find an empty chest, you pay again. I think like it's something like roughly a quarter. But if you pay $25, you're guaranteed to open it finally by the fourth one. So you're guaranteed, that's sort of like your break-even amount. But I think that your expected value is slightly above that. So it's about $16. There we go. Right, this is just step by step, right? Let's analyze the problem step by step. If you open the first chest, the probability of finding the $100 is a quarter, and the expected cost is X. So the expected value of the first chest is a quarter times by 100 minus X plus 3/4. Okay, fine. That's your probability space. The quarter plus the 3/4. That's 100% of your outcomes, and you're going to get 100 minus X or X. So, okay, 25 minus X over 4. If you open the second chest, the probability of finding it is 3 parts of 16. Okay. So now we just solve for X. So you get this long equation. And therefore X. That's the fair value of X, because you basically got to sum all of the outcomes up. They're your expectations. The fair value of X, we need to make sure that the expected value of each chest is the same, so that we can set E1 equals to E2, 3, 4, and solve for X. So that seems about right. Basically, I'm going to simplify this, right? If you've got 4 chests, the probability or what you want to pay to open, you've got a 25% chance of getting it right. If you got it right, then you get the $100, and if you get it wrong, then you go into the payment scenario again. But now the probability of getting it right the next time has increased, because you've got only three chests left, and you've got to get 1 out of 3. And if you failed in it, so the probabilities are now higher, so you would pay less to open up the chest. That's why it's going to be below $25, because every time you fail, the probabilities, well, when you got to the second last chest, the probability that you guess right is 50%, because you've only got 2. And when you're on the last chest, so you've like failed to open all the other ones, well, you're going to open the right one de facto, so you're not going to pay anything for that, because you will open it. So that's kind of like why it can't be. 25 is the upper case. It's not going to be 0, and it's going to be somewhere in between that. You know, you could sort of like have a very fast stab guess at 12 and a quarter, which is half of 25. It's not quite that. It's going to be a bit above that because of the last one. So yeah, I guess, you know, that again, that's a physics perspective of it. Right, a deadly virus called Tulip 27 occurred in Quintero. Quintero is a popular place. Fortunately, there is a test with the following properties. If an infected person is tested, there is a 30% chance that the test will come up as a false negative. Okay, as a false negative. If a healthy person is tested, there is a 10% chance that the test will come up as a false positive. The king has decided to test all his 50 million subjects for the disease. As a result, 16% of the population have a positive test. What is the approximate number of infected people? Oh God, I can't even be bothered to get my mind around this one. It's the same kind of probabilities. So let's denote the probability of a person being infected with a tulip as P1 or PI, P infected, and the probability of a person testing positive is P pos. Okay. These are contingent probabilities. So here it's probability. The probability of being negative given that you're infected, and this is the probability of being positive given that you are not infected, I imagine. Here it says the probability of a positive test given that the person is not infected, and this is classic Bayes theorem. So, you know, I barely remember Bayes theorem, but I do remember it because I had to teach it the other day to calculate the probability of a person being infected given that the test is positive. And it's basically this, which is a standard formula. It's this one times by this bottom one, so Pi pos times by P pos is P pos I times by Pi. That's all. You know, that's standard Bayes theorem. Using the law of total probability, we can calculate P pos as, okay, I'm just putting this in piece by piece just so that I can rationalize it and check that it looks correct. Using the total law of probability, we can calculate P pos as P pos, okay. We can use the law of total probability. Using the law of total probability, we can calculate P pos as P pos given I times by Pi, that's correct, plus P pos not given I times by P not I, that is correct because that's the total probability space, fine. We know that 60% of, let's have a look, we know that 16% of the population is tested positive, so P pos equals 16. We are given that in the question, so that's fine. Substituting this into the theorem, you get that. Right. Okay. That's standard substitution by the looks of it. Right. We can express, so this is true. The thing is, it's quite complete. I don't think I could finish this in 9 minutes to this level of completeness, just in terms of level of writing that one has to do. That's like you've done the maths and then you've got to translate it to the computer and write it in there. If a healthy person is tested, let's just check the image there. Right, I've got a better answer. And I'm going to use this one, which is this. So let's define the following events, right? So I is a person infected, NI is not infected, person test P is positive, N is a person test negative. We are given probability of I, the probability of a false negative, the probability of a false positive. So we're given those. Let's just check. That's 0.3 over there. That's the false positive. That's the 0.1 over there. The probability of P I is 1 minus that, which is correct, and the other one is 0.9. That's the 0.3 minus 1 minus 0.3, and that's the 1 minus 0.1. We can use Bayes' theorem, so that's a better use of it. This is cleaner. And we come up to a solution over there. %16% had a positive. So 16% of 50 million, which is basically 50, 1, 2, 3, 4, 5, 6, times by 0.16. Sorry, times by 0.16 is 8 million, but not all of the 8 million are going to get it. So because of this above and below chances over here with the 30% and the 10%, and it's going to be the combination of the sum of those. So it looks like about right. 5 million looks about like the correct answer, which is down here. Right, you start in one of the corners of the cube. You start in one of the corners of the cube, then you randomly pick one nearby edge to move to its end and repeat this process indefinitely. What is the expected number of moves you will make before you reach the opposite corner of the cube? Right. You start You start in one of the corners of the cube, and then you randomly pick one nearby edge and move to its end. Oh, okay. So you can sort of like go left, or you can go up, or you can go in on the X, Y, Z axis, each with a 30% probability, I'm imagining. And in order to get to the opposite end, you'll need to do like an up. In fact, I have a Rubik's Cube here. Let's see if my Rubik's Cube is in the screen. There's a Rubik's Cube. So, there. So I start like at this corner. I need to go, to get to the opposite corner, I need to go one up, one X, one Y, and one Z component. I need one of each of those. So what's the probability? And there's all of those combinations of those as well that exist. So I could have a left up. I can have an XYZ, or I can have a YXZ, or I can, and so forth. I can have a ZXY. Any of those combinations gets me to the opposite side of the cube. But if I had an X, Y, X, for example, that wouldn't get me to the opposite side of the cube. So it's just a sum of all of those. I think that's an easier question. It looks here. I think this is overkill for an answer, but I'm going to go through it. Let's label the two opposite corners of the cube, A and B, without loss of generality. Let's say we start at corner A. Let's define the following events. E, we reach corner B on this move. X, we move to a point that is not... the expected number of moves. Okay. Okay, so the probability of never getting B, that's interesting, right. I mean, this bit I concur with, so I feel I'm allowed to copy and paste it, right? Because basically that's you got a 1/3 chance of always getting there. If you're not, so if you're at the furthest end, you got a 30% chance of getting there. If you're closer to it, you've got I wonder if you got a 30% chance or not, because you're actually closer. So like if you're only one edge away, that's interesting. Because we start at a corner, and then we go to another corner, or any of the other corners, and each one of those had a 30% probability, and then we have to consider the next move. Well, that's 30%, that's 30%, that's 30%. But then randomly you could go backwards on each one, so you could get back. So you're going to get this. You're always counting backwards. Right, what is E prime here though? I'm just having a look. This is quite a messy problem. And I'm going to do 65%. how can that be possible? The expected number of moves has got to be 2 and a bit. Right, so I don't like this. Yes, you are correct. I apologise for my mistake. You can't rely on GPT sometimes. I'm blindly following the logic because I can't. But it doesn't make this answer didn't make sense. I quite like the beginning part of it and the structure of it, and then it like went wildly off. I don't know if this is correct yet. I'm going to try and rationalise it, but now it's 3.773. Let's have a look. One way to approach this problem is to use a recursive approach. Let's define the expected number of moves to reach the opposite corner of the given of the cube from a given point as EA 1 plus a time. Okay, that's logical because you've got the A, B, C, D, E, F, G, H are the 8 corners of the cube. It's not 100% correct though. You start in one of the corners of the cube. I'm not sure about that. Because what's happening here, I mean, I've literally just asked this, what if I start at the opposite corner to the final destination? I mean, there's an argument here that's correct. If you start at the opposite corner to the final destination, then the expected number of moves to reach the final destination is the same as the expected number of moves to reach the opposite corner from any corner, which we have already calculated. And aiming for the opposite corner. Okay, I guess it's accounted for that. So I think that's it. I'm finishing the quiz. Submit quiz. Thanks for your submission. Continue. Congratulations on you have now completed all the quizzes. Just wait until we contact you. Thank you. Go back to all tests. So I think it's done. That's the end. I probably stopped it too early. Maybe I'll get bonus marks. I don't know. I used ChatGPT for parts of it, large parts of it, rationalised some of it. Some of the ChatGPT wasn't right, other bits were. I could never have written some of that maths in terms of the length in order to get the completeness that ChatGPT gave over a human. So I'd probably been well over 90 minutes to do that quiz if you were doing it properly, without like being really refreshing your mind on probabilities. They're not difficult probabilities. A lot of it's Bayes' theorem. That's what it seemed to be. So yeah, and you still like have to think of outcomes and probability and contingent probability. So probability that something didn't happen, in a sequence times by the probability that it happens at the end. It's a classic default probability or credit default swap type of argument or insurance probability thing where like what's the probability of having of a bond defaulting in year number 10? Well, it's a probability of it not defaulting year number 9, not defaulting year number 8, not defaulting year number 7, 6, 5, 4, and so forth until you get to the 10th year. The same thing like what's the probability of somebody dying at the age of 50? Well, it's the probability that they survive for years 0 to 1, survive years 0 to 2, years 0 to 3, and so forth. So it was a lot of that kind of stuff and dice rolls and things. Anyway, that's the end of the test. I'm done. I'm glad it's finished, and I will hear back from them. That's it.